Thank you so much for coming to the transport seminar. Welcome for those who are joining us online. And we have also the students here in the class. Today we have Andre Carrel from the Ohio State University. And I've been following Andre's work for several years now, since he was a PhD student and he was doing some of the pioneering research in the area of public transit market segmentations and understanding and linking public transport services to operations. So it's a pleasure to see you back and to hear more about your research and your new stuff you have been working on recently. Thanks, Andre. The floor is yours.
Thank you very much, Ahmed. It's a pleasure to be here. Thank you very much for the invitation. All right, let's get started then. So today I'm going to talk to you about the connection between quality of service and transit ridership. And so some of this work, not everything I'm going to show today, but some of this relates also to the pioneering research that Ahmed referred to just now in the introduction. So I am an associate professor at The Ohio State University. I have a joint appointment in civil engineering and city and regional planning. And some of this work is work that I'm going to talk to you today about is work that I did while I was at UC Berkeley. So that's the San Francisco connection that you're about to hear a bit about. So first, by way of introduction, the title of this talk is on service quality. But really, when we talk about service quality, what I'm mostly going to focus on here is transit reliability. Now, when thinking about service quality, I tend to like to lump the different dimensions of service quality into two separate groups. One that I call operational service quality, which refers to travel times, the reliability of travel times, the accessibility of service, the provision of information, etc. And one group that I call the travel environment, which refers more to the environment that the transit riders move around in. So the cleanliness of the vehicles, of the stations, levels of crowding, perception of safety, etc. Now, qualitatively speaking, we do know that reliability and actually transit service quality more broadly does affect ridership, right? So higher quality service, more reliable service tends to attract more riders and vice versa. But what we know at this point is mostly a lot of the prior studies have been qualitative. And of course, we also all kind of have this anecdotal evidence, probably, where we've heard stories from friends or family who had some sort of terrible experience on transit, and therefore we're looking for alternatives, bought a bike or something like that. Now, I've long been trying to put some numbers to this relationship and quantitatively understand the links between service quality and especially reliability and transit user behavior, i.e. demand and ridership. This is actually quite challenging because the behavior changes we're talking about, they're difficult to detect. They can be gradual, and I'm actually going to show some numbers that sort of seem to show that, or they can be fairly abrupt. Some sort of bad experience that somebody has and then decides, well, this is it, this is the last straw. And in addition to this, one of the challenges that we have is that current demand modeling approaches to reliability are actually very limited. So let me talk a little bit about this briefly. The standard way, the most common way that travel demand models, mode choice models, incorporate reliability of any mode is usually just through the standard deviation. There is a more advanced technique called the scheduling model, but it requires a ton of very detailed data that we typically don't have on hand. And so the general way to do this is just to add the standard deviation of the travel time on certain modes, on mode I, into the utility equation of our mode choice model. Now, this is a fairly crude representation, and it comes with a few problems. The first is, well, it doesn't actually account for the fact that maybe not all sources of variance are experienced equally, right? Certain delays, where they occur will make an impact, or when they occur. And then secondly, like I kind of alluded to before, that sometimes behavior changes may actually be triggered by certain experiences that people have while traveling. Lastly, I also want to say that these are aggregate high-level representations of the performance of the system or of a route. And we have to keep in mind that actually individual decision-making of individual travelers is based on their personal experiences, right? So whatever my mode choices are today, or could also be my route choices, departure time choices, that is largely informed by previous choices that I made and the outcomes of those choices. And so in reliability research, there's this concept of the personal travel time distribution, which is basically the travel time distribution that I, as a traveler, develop through my experience of repeated transit use or use of some other mode. So what I'm getting at here is that there's kind of a cyclical nature of travel behavior. And so down here, let's look at this diagram. It's a simplified diagram, but what I'm trying to show here is, we have what the transit agency can influence and can control. So we have certain inputs to their service. We have the infrastructure that's available, the network that's designed on top of that infrastructure, and then a timetable. And those inputs together produce the day-to-day operations that the transit agency provides. That's our transit system. So that's what the agency has control over, right? Now, as an individual traveler, I go about my day-to-day travel using the transit agency, and as a function of these operations, I experience a certain level of service quality. Now, that experienced service quality, through some sort of cognitive processes that I've got a question mark on here right now, so some sort of cognitive processes will somehow produce future decision making. It will inform or influence my future decision making. So it's an indirect link here between operations and decision making. And what's going on down here with these cognitive processes, this is outside of the control of the transit agency. So I have two parts to this presentation today. In the first one, I'm going to present to you some initial research results that are trying to get to the bottom of these processes I'm talking about at a very individual level. Then I'm going to move on to part two, and in part two, I'm going to step back and have a look at the bigger picture of why it is important to conduct research on the link between transit reliability and ridership levels. So these initial research results, I'm going to introduce you to the original study and then the results that came out of this study, the San Francisco Travel Quality Study. So this was a 6-week study involving 856 participants, which were all frequent transit users of the San Francisco Muni system, the SFMTA. And then we did a follow-up survey 12 months later. So the duration of this, it started in late fall 2013 and it ran until early 2015. And the objective of this study was specifically to quantify, with emphasis on quantify, the links between reliability, satisfaction, and transit user loyalty. And so to bring us back to this conceptual model that I started designing in the previous slide, right? We have experienced service quality, which is influenced by day-to-day operations. And then you have decision-making. And we have 3 steps, or we have several steps in between, these kind of cognitive processes that happen. Now, one of the objectives of the study was to actually understand at a more detailed level what might be going on here, and as a good lens for this, as a good mechanism, we identified satisfaction, because that helps us. That's a useful variable to help us quantify the impact of operations on decision making, because it relates to a cognitive evaluation that people make. It's in psychology, people think of this as being a variable that comes from the comparison of the expected and the perceived received quality of service. Also, satisfaction is a very convenient variable because it's frequently already measured and tracked by transit agencies. And so in part, we also were hoping that we would be able to develop some tools here, gaining insights on factors around influencing satisfaction and then influencing decision-making that would help agencies anticipate rider attrition before it happens. So these 3 steps here, we're breaking this down into, first we have experienced service quality. So my day-to-day experience with service quality, that then gives rise to individual trip-specific satisfaction. So this is the satisfaction really coming from that one encounter of me as a traveler with a transit agency. Now, if I'm a regular transit user, I make many such experiences on a day-to-day basis. And those eventually accumulate into a cumulative satisfaction, right? Kind of a global satisfaction that I have with the transit agency's service and the experiences I'm making. And then that global satisfaction is what we think eventually influences longer-term decision-making in terms of mode choice, maybe also route choice on the transit network, and perhaps even vehicle ownership choices or residential location choices. So we wanted to develop models for these individual steps that are numbered 1 through 3 here. Now, the study itself, let me first introduce you to the study design. It was done in close partnership with the San Francisco MTA and the San Francisco County Transportation Agency or Authority. And overall, there was a first initial phase of 6 weeks. The participants were asked to complete 2 entry surveys in Qualtrics. So this was on their phone or computer. And then they were asked to install a survey in a tracking app. And that tracking app then over the next 6 weeks was continuously tracking their location and trying to infer their transit use from that continuous location. Every day, participants were given a prompt at the end of the day, asking them to complete a survey on their phone about their transit travel experiences on that day. So basically the survey asked, hey, did you use transit today? And if so, would you please complete this little survey where you tell us about your satisfaction with the service on this day? And then at the end of the 6-week tracking period, they completed another exit survey on Qualtrics, where they were asked several questions, including things like cumulative satisfaction. A year later, a little bit over a year actually, a year later in 2015, then we did a follow-up survey where we again checked in with our respondents and looked at how they were traveling at that point and what their satisfaction was at that time. Now, while these 856 people were tracking their movements throughout San Francisco, we were also collecting the full feed of real-time location information from all the SFMTA, the entire SFMTA vehicle fleet. Now, the purpose of this was to actually objectively measure the travel time experiences that people were having on the network. And so, taking these 2 large data sets, the tracking data from the individual's phones and the tracking data from the entire fleet of transit vehicles in San Francisco, we had a server infrastructure set up in the background that did regular nightly processing where we tried to match the traveler trajectories to the vehicle trajectories. So you can see that conceptually over here as an example. Suppose we have somebody with their phone and the phone is generating these red location points. And so on the far right-hand side here, you can see, right, we can divide into stasis and motion. When someone is static, carrying out an activity, there are kind of these clouds of location points. So maybe this is their home, and then they start a trip. So they walk down to a transit station, and then we see this kind of cloud of points here that represents the waiting time at the transit stop. So from this, we can infer how long this person would have waited at the transit stop. Then a transit vehicle comes along, and these are the green location points. And then all of a sudden, we see the phone and the transit vehicle moving in parallel with each other, right? So now we know the person is on board the transit vehicle. And from this, we can derive the in-vehicle travel time. Maybe here we also have an instance where both the vehicle and the person are idle or stationary for a moment. That would indicate an onboard delay. The person is on board, but somehow the transit vehicle got stuck. Maybe in congestion or because of a door malfunction or whatever that is. And then eventually these lines are going to split again. And so from this, we can infer where the alighting stop was, where the person got off the vehicle, right? So the idea here is that with this system, we could automatically observe and infer at a very detailed level all the components of the transit travel times that people are experiencing. So in addition to this, we actually wanted to know, well, how good or bad was the service? And so to do that, we compared it to the schedule to understand how the service would have been if it had been on schedule, what this person could have expected on that day. So we compared the measured travel times to the expected travel times based on the schedule. So that's based on GTFS. Now that sounds fairly simple to do, but there's actually, the devil's in the details here. Because that means we have to construct, right? We have an observed trajectory, an observed assignment of a traveler to certain vehicles, but then we also have to come up with a hypothetical assignment if the service had been running perfectly on time. And so If you look at this figure down here, we can see the axis of time, and let's assume that there were 3 scheduled departures, S1, S2, and S3. Now, what was observed actually were 2 departures. So there was one bus that departed D3, which exactly matches the schedule, but then there was this bus D2 here, which doesn't match any of the scheduled departures. And then the little round dot here, that's when our traveler showed up at the bus stop and then boarded bus D2. Now, when you're trying to construct this hypothetical assignment to determine what the person could have expected had the service been on time, that means we have to determine whether they actually would have been taking or would have wanted to take S1, but they saw that no bus was arriving, so they didn't go to the stop, or would they have taken S2, but they just happened to show up early and they got an earlier departure, or they got a departure that was actually earlier than what would have been scheduled. And so there are a lot of kind of detailed decisions that one has to make here to try and assign a person to a hypothetical trajectory. And so we had a whole system running in the background with a set of, effectively, there's a set of decision trees that try to go through different possible scenarios and ways in which a person might have scheduled their arrival at the transit stop. Also depends on the frequency of service itself, of course. So that gave us the objective measures of experienced and expected travel experience. And then we had the trip-specific satisfaction, right? So now we're making this jump from the experienced service quality to the trip-specific satisfaction. And now this is basically a subjective assessment of the quality of the service. So at the end of each day, there was this mobile survey where people were asked, hey, if you used transit today, how satisfied were you with all these different aspects of the service? And so the items that they were asked about are shown here: satisfaction with operations, so real-time in vehicle, wait time, in-vehicle travel time, the reliability of service, and the real-time information system. And then the satisfaction with the travel environment, the cleanliness, the crowding, the safety, and generally the pleasantness of other passengers on board. So the assessment, it was all 5-point Likert scales here from labeled with a frowny face and a smiley face, so people could evaluate their experience on that day. Now, just looking at this, before we move on to fill in the following steps of this diagram shown at the bottom with the cumulative satisfaction decision making, let's look at what we can just learn from this. So up here at the top, you have a figure that shows the level of satisfaction reported by people with their trip. The dark part is very dissatisfied. The lighter shaded gray here is very satisfied. And so here we have the satisfaction as a function of the experienced wait time, the transfer time, and then the in-vehicle travel time delay. So these are cases where a vehicle somehow got slowed down in congestion or got stuck, especially in San Francisco. There are often problems with the light rail system when entering the underground tunnel sections, where there can be some congestion of transit vehicles, and therefore vehicles have to be held back before they enter the tunnels. And so then the passengers are basically just trapped on board, waiting for this vehicle to proceed past the red light. So what we could see here, just from comparing the experienced travel times here to the levels of satisfaction reported post-trip, was that where and when a delay was experienced by someone really matters. And in this particular example here, we can, for example, see the considerable impact of in-vehicle delays. And that 1 minute, the marginal effect of 1 minute of in-vehicle delay is quite a bit bigger than that of wait time or transfer time. Also, separately, we observed some complexity here. Now, I'm summarizing a lot of research into one bullet, but basically the complexity we observed was that when people provide their daily satisfaction with the service, it turns out that we were able to identify lagged effects in that day-to-day satisfaction. Lagged effects meaning that, say, if I had a bad experience yesterday using transit, I experienced a delay, that might still affect how satisfied I say I am with the service today, even if that service ran perfectly on time, right? So there's kind of a sort of a hangover effect, if you will, from a bad experience on previous days, or a good experience, if you will, that can set the bar higher, right? Now, the issue of this, what we're taking away, we were not expecting to find this, but in the as it showed up in the data afterwards, this actually has implications for future survey design, where if somebody, including a transit agency, might be wanting to measure day-to-day or trip-specific satisfaction with transit service. Now we'll move on to the next step. So let's talk about, right, we have this day-to-day travel satisfaction, and then that somehow accumulates into cumulative satisfaction. So the cumulative overall satisfaction, that's what we measured both in the entry and the exit surveys. And we can see in the figure down here, the satisfaction with these various items that I just showed you previously on the screenshot of the mobile survey, charted from the entry survey to the average levels in the mobile survey, the peak, the end, and then the exit survey. And its operations, and on the right is onboard environment. And so interestingly, what we found is that over the course of these 6 weeks, the changes in overall satisfaction were actually fairly small. So there's very marginal differences here. We also found that the overall the satisfaction that they reported in the online surveys, kind of the retrospective overall satisfaction with these various items, was generally lower than the average trip, even if you look at the average of how they rated every trip that where they responded to a survey, their global rating was still lower. This held, for whatever reason, I don't actually have a hypothesis why, but this held for all travel time components except in-vehicle travel time. So what this is telling us, at a minimum, is that there seem to be some cognitive biases here, that in some way, when you ask people to focus on specific travel, they might report good experiences, but in the end, when you ask them globally to evaluate the service, you're still going to get a lower rating than what they would have reported on average, or the average of what they would have reported on a day-to-day basis. What those cognitive biases are, that still remains to be understood. And so here, this is the one, I would say, this link, this second link from trip specific to the cumulative satisfaction, is what I personally, as the person who conducted this study, still consider kind of the weakest link, that we didn't actually manage to really nail down what that connection there is. And so more research on this is needed, and I'm actually currently preparing for a study where I'm hoping to get more to the bottom of this. Now, let's talk about the last link. So we have the cumulative satisfaction, then we're going to move on to decision-making, right? How does this cumulative satisfaction affect my willingness to continue using transit in the future? And so the survey itself, the exit survey, actually had multiple outcome measures to capture kind of initial stages of change. Those outcome measures, they were based on established frameworks in social psychology. So over here, you can see this is the model of goal-directed behavior. It's extension of the theory of planned behavior, in case you're familiar with that. But effectively, right, we want to measure behavioral intentions or behavioral desires on different timescales and take those as indicators of what people are going to do in the future. And when I talk about what people are going to do, it's really, we were interested in how are they going to use transit in the future? Are they going to continue using it at the same level as now? Are they going to increase their use? Are they going to decrease their transit use? Or are they going to stop entirely? So we had these behavioral intention measures, but we also had the follow-up survey, right? So a year later, we went back, and for everybody who still was living in San Francisco, we could directly ask them about their transit use at that time. And here comes the kind of the shocking statistic of what we found with these 856, well, actually not 856, right? Because we excluded people who had moved away. But with the ones that remained in San Francisco, compared to the time during the study, 44% of those respondents in one way or another were reporting a lower transit use frequency than they had during the study about a year to a year and a half prior. So that's 44% of everyone. 11% only, though, had actually stopped using transit altogether and shifted to other modes, to bike, to walking, Uber, or had bought a car or were using a car, right? So those 11% there stopped using transit, but the majority, the 44% of those who shifted, they were still transit users. They had just reduced their frequency. And so one of the direct takeaways from this is loyalty. If we talk about transit user loyalty, we really need to be considering the frequency of transit use, not just whether they're a transit user or not. Because what I'm taking away from seeing this is that, you know, mode shifts really do seem to be a gradual process. It's not that from one day to another, generally someone just decides, you know, I'm going to change my lifestyle, I'm going to stop using transit, I'm now buying a car and I'm going to be a car user. It's really that this is a more gradual process where individual trips to certain destinations get replaced with other modes. Now, here's the other thing. We had the intentions that people had reported a year prior. It turns out that actually only about half of our respondents had correctly predicted their future behavior. So this is actually a major intention behavior gap, right? We have people saying how they think they're going to travel in the future. And then we go back a year later and it turns out only about half of them were right. This might be not unexpected if you're kind of familiar with the psychological literature on this intention behavior gap, but it's kind of an indication that the sorts of measures that we sometimes use about intentions of future transit use are probably not all that good measures. So let's first talk about the connection between satisfaction and observed behavior. So we developed some choice models to relate satisfaction, so cumulative satisfaction at this point, to future decision making. So basically what we observed of these users a year later. And so over here, you can see the model structure. I'm not going to go into a lot of detail on it, but it's an integrated choice and latent variable model. We tried several different model designs. Effectively, very robustly, they could show us that there was a very clear link between the satisfaction with transit that somebody reported at the end of the study and their behavior a year later, i.e., how strong of a transit, how much of a transit user they still were, how frequently they used transit. The other thing that we found was that these changes in behavior were really primarily driven by their satisfaction with operations. So satisfaction with travel times and reliability, not so much by satisfaction with the travel environment. So I'll say this in a kind of purposely an overdramatically way, but that kind of could lead us to say, well, it seems like as long as the service is running on schedule and it's reliable and is frequent, has acceptable door-to-door travel times, it matters less to people like what state let's say what the cleanliness of the vehicles there is or how crowded they are. So we really kind of have this dichotomy here. What we can do with a model like this is we can derive guidance for transit agencies, such as what's shown here in the bottom left, right? Baseline satisfaction, we had the 44 to 55% of people who ended up leaving the service after or having decreased their use after a year. So we can put some numbers to this now with these models and show the agency, hey, if through improvements to the service, if you can raise the satisfaction by, let's say, +1, there's one standard deviation, here is what your future retention could look like. Okay. Now, also for those who had actually reduced their transit use a year later, we directly asked them about the reasons, right? So it was not just the satisfaction model; it was also we had some self-reports here, and so by and large, they just end up confirming more or less what I said on the previous slide, which was up here. Well, let me actually start down here. At the bottom, you can see lifestyle change, right? And that is by far the most frequently named reason. The shading here is very influential, somewhat and moderately influential. That's by far the most mentioned reason. And of course, we know that this can lead to mode shifts. But if you then look at the attributes of the service, we can see that above all, reliability really stands out as the most frequently mentioned reason for people having reduced their transit use or quit using transit. And then followed by, we have various other travel time measures. But as a group, you can see that the travel environment, the onboard environment, actually kind of comes in at a lower level. Okay. Now I mentioned, right, that we saw this gap between what people had predicted they were going to do and what they actually ended up, their transit use that we measured a year later. And so I found this kind of as a side note, kind of interesting to look into what were the key factors that led to correct versus wrong predictions. So specifically, I was interested in two groups here. First, who were the ones who said they were intending to continue using transit as usual, but later we found that they had reduced their transit use, right? So these were the people who did not see their transit attrition coming, if you will. What were the key factors? So there were multiple factors that we identified, but kind of the key factors that we found were, first of all, higher transit use frequency. So the more frequent riders were more likely to have reduced without having predicted that. If you think of it, this kind of makes sense. Sure, these are the most loyal riders, but also the higher your transit use frequency, the more room you have to actually reduce, right? So this is just kind of a numbers issue. But then also households with greater car ownership, those were the ones that were more likely to have these unpredicted instance of attrition, and generally smaller household sizes. The way I'm interpreting this is when you have a smaller household, you have fewer people who are competing for the household vehicles, right? So it's easier for me to make a lifestyle change and start using the car more, for instance. Then we had another group who had predicted that they were going to stop using or reduce their transit use, but in the end, they didn't follow through. So we went back a year later and they were still using it at the same rate that they were using it during the study. Well, who were those households who did not follow through? Key factors here, maybe not unsurprisingly, zero car households that lacked the alternative, the car as a readily available alternative. Also greater age. The older participants were, the less likely they were to make such a shift, even if they wanted to make it. But then also having a transit pass turned out to be a influential factor. So having a transit pass, right, those are the ones that are kind of more committed to the service to begin with versus pay-as-you-go customers that turned out to be those that were more likely to actually follow through on a stated desire to stop using or reduce their transit use. So what have we done with this first study or this first set of studies, research? Well, the contributions are at a high level, a demonstration of a computational system that allowed us to track people's transit travel diaries at a very detailed level, including all the components of travel time. Then we were able to quantitatively, modeling-wise, link experience travel times, i.e., right, directly coming from system performance, to people's day-to-day satisfaction. And we were able to quantitatively link the cumulative satisfaction to mode shifts later on. This missing link here, trip specific to cumulative satisfaction, well, we do have some indications here of the directions this is going. We saw some cognitive biases in the cumulative satisfaction, a little understanding of the dynamics here, but further research needed. Now, this is a first study, but there is so much more to do. We need more research on a lot of these aspects. We need to, for example, better establish the causality here. What I'm talking to you about now is a 6-week study and then a 1-year observation gap. And then we went back and asked people again a year later. A lot can happen within a year, right? So in order to better establish causality, we really need to have some better tracking, more detailed data on people's mode shifts over time. Secondly, we need to do research. We need to perform some research that links specific types of incidents and delays to satisfaction and behavior, which would really allow us to identify triggers of behavior change. And then we want to basically better understand formation of cumulative satisfaction and understand how quickly people, passengers adapt to changes in reliability. What are the timeframes that are involved here? So with that said, I'm going to take a step back now, away from the very specific transit user behavior research. And I want to introduce you to part 2, in which I want to talk more broadly about the potential impact of future research. And I'm saying this from my perspective. Now, at The Ohio State University, I don't know what the funding situation is in Canadian universities, but for us at least, I'll say, it can be kind of difficult to convince funding agencies or public agencies to fund research into public transportation reliability and user behavior. And so what I'm trying to do here is also make the case for the importance of that. So the overall topic under which I want to introduce this is the idea of transit state of good repair, right? We want to maintain, overall, we want to maintain our public transportation systems in a state of good repair. But we all know the reality. Agency budgets are constrained, and agencies have a lot of competing needs and projects. There are capital projects, and then there's preventive maintenance. And so in any budget cycle, a transit agency will go through a set of cost-benefit analyses and try to understand what are the relative costs and benefits of the capital projects, preventive maintenance projects that I could invest my limited budget in. Now, as a whole, we're not doing very well on the state of good repair. Back in 2021, this was the most recent number I could find, the American Society of Civil Engineers estimated that transit agencies in the US had a SGR, state of good repair backlog, estimated about $176 billion US dollars. And over the 10-year period here up to 2017, the US Department of Transportation had actually rated a fairly large number of, or actually a shockingly large number of transit facilities, of systems, and of vehicles as being in poor condition. So we're talking really about asset deterioration due to a lack of maintenance, due to deferred maintenance, and not keeping them in a state of good repair. And what we know is, even if we take the passengers out of the equation here, asset deterioration leads to deterioration in service quality, right? So an absence of state of good repair, that results in increased vehicle failures, increased infrastructure failures, and both of those things directly produce unreliability of the service. This also yields a lack of spare capacity, right? We have more buses out being repaired at any given time, and that lack of spare capacity produces more crowding, produces service gaps. And then we also get slow zones on rail networks. For those of you who have been, or at least at some point, in the Chicago area, that was a big problem on the CTA. Many slow zones that had been implemented to protect the track infrastructure that was aging and was in dire need of repair. And then, of course, we also have visual, vehicle, and facility deterioration and overall less comfort for the passengers. So now, what I just talked to you about in the first part of this talk is about the link between service quality and reliability and ridership, right? And so we can make a direct connection here and say asset deterioration will lead to mode shifts away from transit. We're going to lose ridership if our system deteriorates. And so conceptually, we can see this down here, right? We have the asset condition going from very good condition, then we have a gradual deterioration. And so at some point, there would have been an optimal maintenance point. If we don't maintain it, then at some point, there's a threshold where it deteriorates past a point where it's starting to impact ridership. So it's starting to create unreliability, it's starting to create a poor travel environment, and so it's going to affect ridership, right? And so if we look at this conceptual ridership trend here, maybe we still have kind of an increase or at least flat at the beginning. And then once the assets deteriorate past a certain point, we will start losing riders because of that asset deterioration. And so if we talk about the benefit of maintenance, benefit of state of good repair, it really is the difference here between what we could have the ridership levels we could have maintained and the ridership levels that sort of the drop off that happens here if we don't maintain our system. So with that said, though, we know that our ability to model such shifts is extremely limited due to a lack of research, right? So because our ability to do this is so limited, that means our ability to quantify the benefits of maintenance and state of good repair is extremely limited. So that led us to design a research project. I did this with my student, Yushen Wang, who is now actually at Poly Montreal. And so the thing is this, right? Even if if our demand models are very poor at predicting people's reactions to unreliability, in practice, somebody's going to have to make demand forecasts in order to optimize asset management. However, what we're just going to get is a large variance in those demand forecasts because of the uncertainty and the inaccuracy of these ridership impacts predictions. So the research project that we designed, the overall objective here was to take this variance, to take the resulting variance in the quantified benefits of state of good repair projects, right? If you go and look here, if I am at the beginning and I'm trying to predict what's going to happen if I don't maintain my system, based on what methods I use or how good my even so flawed prediction is, I'm going to end up at very different points here, and that's directly going to impact what I think the benefits of maintaining my system are, or the costs, if you will, of deferred maintenance. So we want to quantify the variance of the projected benefits that can be attributed to the uncertainty of travel demand impacts. And deriving from that then to state some research needs. How can we reduce this uncertainty in projected benefits and cost benefit evaluations? So in order to better understand where I'm going with this, let's look at this conceptually, because it's actually kind of a complicated sequence of events here. So let's say we have a transit asset that deteriorates. Now, the deterioration itself is going to cause agency costs, but it's also going to cause unreliability. The unreliability causes ridership loss. That produces lost fare revenue. That's a cost to the agency. But some of those trips that are lost, they're no longer going to be made. Other trips are going to shift to the automobile, at least in North America for the most part. That's what happens, right? Now, the automobile trips, the additional car trips that are generated this way, they will cause social costs and user costs, right? There's an environmental impact here. There's a social impact. But how big is that impact? So if we want to quantify that, because that impact, if we can avoid it, is a benefit of maintaining the transit system in a state of good repair, right? So in order to quantify this impact, we need to know what are the general characteristics of car trips in the metropolitan area, how long are they, what's the occupancy, et cetera, and how are we going to value those impacts? What is the cost that we think a pound of CO2 emission, a pound of NOx, the cost of additional noise, cost of congestion, et cetera. So we have to attach some sort of monetized, some sort of dollar value to these impacts that are being caused by the additional car trips. And then, on the transit side, we maybe also have additional transit emissions because we're not replacing an aging vehicle fleet, for example, and that too will produce social costs, which are a function of how we value them. So the benefits of maintenance are really in the avoided social and user costs, right? And we want to go in and look at, if you think of this whole chain of variables here that interact with each other to produce the costs, which of them have the greatest influence on the state of good repair, the benefits of the state of good repair? Now, there is actually some guidance for transit agencies. It's a TCRP report number 206, guidance on calculating costs and benefits of transit SGR programs. And with this report comes an Excel tool for agency use. It's called the ROI calculator. It's an Excel tool, and it allows transit agencies to compare an investment case, which is basically the maintenance state of good repair case, versus a base case, which is deferred investment. If I don't make it and I let my system deteriorate, right? Now, critically though, the user needs to input projected changes in travel demand or accept some sort of default value that's in the calculator. And that default value too, there's a ton of uncertainty. I would know because I put it in there. So with that, the ROI calculator then allows people to calculate the costs and monetize benefits of an SGR investment. So what we did then is we said, okay, we'll just take this. We'll use this ROI calculator as a black box model. And we want to look at the variance that we observe in the calculated benefits of these SGR investments. And figure out how much of that is due to the variance in travel demand forecasts. So to do that, we conducted a global sensitivity analysis using a method called the Sobel method, and the Sobel method is, it dissects the variance and looks at direct effects of travel demand variables and indirect effects through the variables that travel demand interacts with, right? Think of what I showed beforehand with, like how do we value the costs, or what are the characteristics of car trips of the people who we lost from transit, right? So all of that interacts with travel demand to produce certain benefits or costs. And so we want to try and decompose and disaggregate this. So the Sobel method varies the inputs of all selected variables at once and then decomposes the variance of the benefits into partial variances and attributes them to individual variables. So the variables that we looked at, and this is connecting back to this diagram that I showed you previously, this is just the actual set of variables from the ROI calculator that we considered. So we have two travel demand variables. First, a forecast of how many people we're going to lose from transit, and then mode choice, basically how many of those are going to shift to the automobile. Then we have the characteristics of auto travel in the metropolitan area, and then we have the values that we attach to environmental emissions, congestion, to emissions, environmental costs, congestion, and user costs from operating a car. Now, the environmental costs, what we have here are both local environmental costs, like direct health costs, and the cost of greenhouse gas emissions. All the other variables were held constant. Now, we had to come up with some scenarios here to analyze. So we generated a set of 37 state of good repair investment scenarios. They were hypothetical, but they were realistic. We based them on agency data using data from 16 of the largest transit agencies in the US. And overall, we developed 4 types of scenarios. So one was bus replacement, basically replacing an aging bus fleet. Second was rail vehicle replacement, could be light rail, heavy rail. The third was without replacing anything, just increasing vehicle maintenance expenditures. And the fourth one was guideway rehabilitation for rail systems. So what did we find? First, overall, the results that we found here. On the left-hand side, we have 2 tables. The top one shows the standard deviation of the benefits. So this is like, how much variability am I getting in my benefits due to uncertainty in travel demand and everything it interacts with? And how big is that variability, expressed as a standard deviation, as a function of the overall cost of the investment? And so what you can see here, these percentages, basically they show us that there are large impacts that we get from this uncertainty in travel demand models, or our inability to appropriately forecast impacts of unreliability on economic efficiency measures. In some of the cases, some of the scenarios we had, they could actually exceed $100 million US. You can see here that relative to the investment cost, the bus replacements are the ones that have the largest variability. Whereas then in decreasing order, guideway rehabilitation, rail vehicle replacement, and vehicle maintenance. Now, this is the total investment cost, right? If we look at just the overall benefits that were calculated to be derived from this project, and we compare the standard deviation of the benefits due to travel demand impacts, travel demand forecasting impacts to those average total benefits, so that's a coefficient of variation, the order in which they appear is a little different, but considering the COV, we see that actually the guideway rehabilitation projects, so this is rehabilitation of rail infrastructure. Those are the most vulnerable to erroneous ridership projections. So I'm going to talk a little bit about the individual variables, and then we're going to step back and see what we learned from this. So first, in terms of the individual variables, first we have the travel demand variables. And those were sort of at the root of everything, right? We have travel demand changes due to unreliability. And then there's this kind of chain of additional events and variables that come into play until we eventually arrive at a cost. So travel demand itself, we found it's consistently top contributor among the top contributors to variability of the state of good repair benefits. And we calculated that having better travel demand forecasts, even kind of a fairly simple representation in the ROI calculator, could reduce the variance of the benefits by 20 to 49%. Also, the mode choice of lost riders was more important than the actual absolute demand reduction. So yes, we're losing people, but how many of those shift to car is actually critical to quantify the benefits of investing in the transit state of good repair. Because of course, using the car imposes a ton of additional social, environmental costs and user costs, right? So that's where those benefits are coming from. Then if we look at the characteristics of auto travel, so once these people we've lost them from transit, now they're using the car, what are those travel patterns like? And so, admittedly, these are fairly high level statistics, but typically that's what we might have to work with at a first cut. And we found that overall these variables had kind of a medium level impact on the variance of benefits. It's nowhere near the impact that the actual prediction of travel demand has. About 10 to 15% is what we could reduce the variance if we just had better statistics on how people are using cars in our metropolitan area. And then finally, social and user costs. So it turns out there's really one that stands out here, and that is the cost of greenhouse gas emissions. And that alone accounts for 10 to 31% of the benefits variance. The range is because of the different types of scenarios that we had. But this is a fairly large one here, cost of greenhouse gas emissions. And this is really a question, right? What do we think the cost to society, to humanity is of an additional ton of carbon dioxide emissions, right? And so the dollar value we put on that actually turns out to be a huge driver of the benefits of transit state of good repair investments or the variability in benefits. The other costs, so the local environmental costs, congestion, operating costs, they had a really low contribution to the variance of the benefits, under 10%. So in other words, if I were to conduct research to better quantify these costs and try to nail them down better, that's going to have very little impact on the SGR benefit estimates. Interestingly, on a side note, the effect of greenhouse gas emissions cost was greatest for vehicle replacement scenarios, lowest for guideway rehabilitation scenarios. So what's the moral of the story here? Well, the first big point that I'm trying to make here is that our lack of appropriate travel demand forecasting methods has major impacts on the assessment of state of good repair investments, but therefore it has a major impact on how transit agencies or public agencies in general are allocating investment funds meant for transit agencies, right? So what we're seeing above all is just a huge variance and possible biases in economic efficiency measures that underlie benefit cost analyses, because we just can't quantify these benefits very well, right? So what that creates is a high risk of suboptimal asset management and transit investment decisions. So we really have an urgent need here for better mode choice models that incorporate asset deterioration and service quality deterioration. So if we could do that, we have the opportunity here to reduce the variance in these calculated benefits and get much better estimates, reduce that variance by up to 49%. Now, one thing that's also kind of hidden here, I didn't put this in a separate bullet, but you remember when I talked about the research needs at the end of the first part, I said one of the things that we want to do is also we need to understand the timeframes involved here. And so this is especially key here when it comes to asset deterioration, because it's a very slow process, right? And reliability deteriorates fairly slowly as well. And so we also need to understand sort of on what time frame are people reacting to this, and are there certain thresholds or certain sort of inflection points where ridership is really going to drop off. In the meantime, of course, this is a huge multi-year research program we're talking about here. But in the meantime, given what we've seen here, I mean, it really is critical to reflect this uncertainty that we have in the benefits that we're calculating for SGR investments, that we present those appropriately to decision makers to make it clear that there's a lot that we really don't know here about the impacts of our investment. So finally, conclusions for both of these studies that I've talked about here. First, we have established that the link between transit service quality and ridership making some headways, but it remains fairly poorly understood. And there really is, following what I just discussed, there are clear and tangible benefits of better travel demand models that can capture transit unreliability and people's reaction to the deterioration of transit system and increased unreliability. And those those tangible benefits in part are also, they have a big financial component here, right? Then, going back to the first study, we found that, well, satisfaction is really a variable that helps us quantify the relationship between service quality and rider behavior. It helps us understand behavioral mechanisms between ridership gains and losses. And it's a convenient variable because many transit agencies already monitor satisfaction. We also found that satisfaction with travel times is key to user loyalty, matters a lot more than travel environment, and that not all delays are created equal, that the location and the timing of a delay that someone experiences really affects their satisfaction and, by extension, their loyalty. And then finally, we also identified possible cognitive biases in the formation of cumulative satisfaction with the system. All right. Thank you very much, everyone. So I don't know whether we still have time for some questions.
We'll have questions, yes. Yeah, we have
Perfect.
time.
Okay.
So much, Andre. Thank you. So we'll start with questions in here. If anyone of you have questions, yes.
Well, the low ridership of San Francisco reduces as much as the service sample in the same period.
I'm sorry,
So was the sample, like the ridership decline in San Francisco in the same proportion as you have seen people leaving the system from your sample?
my very rough back of the envelope, my rough back of the envelope calculation actually says yes. It seemed to be at least the 11% that left the system. Because, so I didn't have access to records showing frequency of use of individual users. But you do recall that I had, right, that 11% of people who actually left the system despite still living in San Francisco. And that 11% actually seems to closely track what we see from usage data from the smart card system of people who kind of stop using the system based on their smart card data.
Let me ask you a question from an online. It asks, was there specific demographics in the survey who more often correctly/incorrectly predicted their future behavior compared to others? So were some gender, like men telling you we're going to do something and they didn't do it in the future, or a certain income group, or any general differences? Or you didn't see any?
Oh, sorry. I did find, so the one that I did call out there in terms of demographics is the age, right? That there was clearly, like, younger users were more likely to jump ship. And that was now, younger users are also more likely to have lifestyle changes, right? That kind of that's a similar stage of life there. But I don't, so there are none that really stand out to me otherwise in demographics. The list that I had on the slide is not the full list. And unfortunately, Anna, I'd have to refer you to the paper there to go look at the actual results. I can't tell you off the top of my head right now what else stood out aside from the ones that I called out.
We'll go back to a question from here.
Yeah, well, just related to demographics, like, was there, for example, like a big change from students who then like graduate, go on to work, so they changed? Like, was that a variable that was observed?
Possibly, yes. I don't have. You're talking specifically about the attrition, right? So the people who,
The people who reduce, like, not change completely, but like.
Right, yes. I cannot tell you that right now. What I can say is that some of the recruitment, not all of it, did happen at a university, San Francisco State University. So, that in combination with also just the fact that it was a mobile phone-based survey, smartphone-based survey, the demographics of the respondents did skew a little bit towards the younger side. Now, whether part of this is students transitioning from being students to young professionals, and in doing that, changing their habits, while plausible, I can't tell you quantitatively how big of an effect that was in the data here.
Other questions here? Yes.
I was wondering how applicable is the study to cities with like more weather changes, because San Francisco's very, I guess, warm throughout the year, but in cities where it's like a more bank break, transit super unreliable.
So talking about the weather, how the findings are applicable in areas where, because San Francisco known to have good weather, right?
Yep. Well, I can hypothesize about that. I think, I mean, you're right, that San Francisco has a fairly temperate climate, and so it's pleasant. It's relatively pleasant to be outside as a transit user any time of the year. My assumption here is, well, on one hand, yes, you probably have some seasonality in transit use in general, but so when the study was conducted and when the follow-up was, that was both in the winter, which does tend to be a little on the rainier side in San Francisco. If we're talking about more extreme temperature changes, I mean, my assumption is that, this is a predictable seasonality for people using transit, right? And so I might have some sort of regular, like I might be a transit user in the summer, and I might not use transit in the winter, for example. I might have some sort of routine. But where I think this becomes a little more interesting is that I will assume that in, say, cities with more extreme winters, for example, that might impact service reliability, right? And so you might have, you might actually be dealing with worse quality of service during the winter months, which then obviously can cascade on to rider dissatisfaction.
Any more questions? I have a question just to wrap things up. It's about the attrition of the sample. So you came back after a year. So
Yep.
how many from the 800 came back to you in the second round? Like
Yeah.
some of them say, I'm not going to answer this guy again.
There's
So
certainly
many were like this.
yes, no, there. So off the top of my head, without going to look again, I want to say so 850. Out of the 850, also, not everyone actually completed the full 6 weeks of the initial study, right? So there was some attrition that already happened there. I want to say I ended up with something in the low to mid 700s of people who actually really completed everything in the first 6 weeks. The number of people who responded a year later is, I think, around 550. So we lost an additional like 200 in there.
That's very good, actually. Because usually it goes from around 30% people only come back and like it's not in some studies I have seen recently. So you're way above 60%. That's 60, 70%. That's great. So there's a big long question came from an expert in Toronto, Brendan Myrie. And he said, in part one, the research is focusing on the frequent riders and found that they are extremely sensitive to variability. But the behavior may be different among less frequent users. For example, I have a much anecdotal experience that suggests that they are most sensitive to the environment and particularly safety, which has become a real challenge. I know several people that have abandoned transit because they are uncomfortable with interaction with homeless people or someone displays mental challenges. That's a big problem that's happening in Toronto actually these days. Do you have any comment on that?
Yes, and I think, and not only Toronto, I mean, I think at least anecdotally, I think many major transit agencies in North America are dealing with these challenges. And this is an excellent point, Brendan. So I think you're right. I think there are probably clear differences in how sensitive people are to different characteristics of the system's performance, depending on their level of ridership. And you're absolutely right that the group that was in this part one study, they were all frequent transit riders. And so because of that, I think also, some of the results that I was showing, let's see, part one, if I can find this just quickly. Okay, well, I'm not here, right? So some of these results that I was finding, I think there is probably some self-selection issue here too, because the people who are still using the system, who are frequent users were frequent users when we recruited them, I would suspect they already kind of have a higher tolerance for the kinds of experiences that you just have using a transit system in a major city on a day-to-day basis, right? And so that might very much have driven the finding here about their, the low impact of their satisfaction. No, here it is, with the onboard environment, cleanliness, comfort, level of crowding. So I absolutely agree with you. If this might look very different for infrequent users, and this too, I think, is something that we just have no data on at this point, or really good understanding quantitatively. And this is a real research need. Yeah.
Thank you so much. Thanks, Andre. It was a pleasure to have you with us today, and the students learned a lot, and we'll be in touch and hope to have you in more seminars in the future. Thank you so much.
Well, thank you very much. If anybody wants to get in touch with me, there's my email address. Also, by the way, I'm happy to make some of the data available. Have some details in this paper that's noted here. and then the set of references. So thank you. It's been a real pleasure talking to you today. I really appreciate the invitation. Some great questions here, and hope you all have a great rest of your week then.
Thank you. Thanks. Bye.
Thank you.